Judgment Day, baby.
Judgment Days. All right, welcome to Nick's defense. I'm going to give you some logistics first, and then I'm going to do a little bit of show today. So the way I run it is sort of typical. We're going to have Nick presents. I told him about 40 minutes. He says he's going to have to run fast to get all his slides in 40 minutes. Okay. Then we'll open up questions to you guys and hammer him with this harder question that you can think of. He needs it. And then we'll dismiss you guys and the committee will meet. So I liked reading Nick's bio. I think some of this I had not. I'm just going to repeat this. It was on his announcement somewhat. But Nick came from, we graduated with a BS in physics and a minor in astronomy and astrophysics from Villanova in 2020. So his last semester during the COVID lockdowns. His first semester here during the COVID lockdown. So that's great. Let's see. His undergraduate studies were supplemented by research in gravitational waves. He did a stint at the LIGO detector in Livingston, Louisiana, as well as the Triumph facility in Vancouver. This is a new one for me. He also says he worked in frustrated magnetism. I don't know what that is. I can tell you after, but I do know, I think, I looked at the paper that came out with that word, so he's a co-author on my paper. The title is Spin Orbit Coupling, Controlled Ground States in the Double Perovskite Irradiance. Does that make sense to you?
Really makes sense to me.
So that's pre-CCOM. During CCOM, this is very interesting. Nick's cruising around looking for someone to work with, and he gets in touch with me. And I show him the work I do, which is related to synthetic aperture sonar, and he's interested. And so he says, I want to work on it. So he shows up, he says, I want to do this topic. It's kind of vague, but you'll find out what that is. And I go, well, I think everything's been done. I don't think there's anything left. Yeah, sorry, he proved me wrong. So you'll see that today. He works fast. So within about 7 or 8 months, this is during his first semester, full course load, he has finished the first part of his work, and he's written a conference paper and submitted it. The second part happened sort of in the second year, and then some tidying up. He, unfortunately, it was too fast for me. He's leaving too early. I'd like him to stay, but he has, since late December, I guess.
Yeah, just about.
Has started a job at Ursa Space System. Kind of related. He's a radar systems engineer, where he's processing synthetic aperture radar imagery and then working on follow-on products. It's kind of staying in the theme of it. So I'm just going to turn this over to you. And thank you. Yeah.
Thanks for the intro, Tony. I appreciate it. I want to start just by thanking everyone on my committee for being very supportive throughout the project and just giving some acknowledgements to all the friends that I've made at CCOM and Chase as a whole. They've been really great and supportive throughout the entire thing. And I definitely wouldn't be able to get through transition semester from COVID and then get through all of this if it wasn't for the people that I met. So yeah, with that, I'll talk about something much more boring and less wholesome, which is quantifying and modeling the effects of internal waves on synthetic aperture sonar. So to start, I want to talk about where the data came from and how we're going to use it. So to start, let's just picture synthetic aperture sonar as just generic imagery where we can get images of the seafloor using it, much like a traditional sonar system. The data for this comes courtesy of the Norwegian Defense Research Establishment and a collaborator, Roy Hansen. And it was all taken off the coast of Elba Island, Italy in 2012 and 2013. The system used was mounted on the Hukin AUV, and it was FFI's HiSATS 1030. This is the AUV as it's getting loaded into the water, and our sonar platform is this little area right here that's used to take the images. The center frequency is 100 kilohertz, bandwidth 30 kilohertz, and a long track and cross track resolution about 4 centimeters. And we'll get into how those play a role in our system functionality later on. But for now, we're just going to start looking at some images that were taken at the survey. most of which are showing the seafloor. Some have aspects of pipe going through it, some sand ripples as well. Here we see another image, and then finally the intensity image. This one is different. It shows an area of seagrass and sand as well. Seagrass are the light areas and sand is dark. And we have some features going through, such as drag lines, things of that nature going through seagrass. Next, we're going to look at some other images, and there's something notably different about these images. We see areas of brightness followed by shadows, and you might think at first that these are sand waves, but they're not. They're actually a result of internal waves or internal wave artifacts. Here we see again in a similar region, and again we see these areas of shadows and dark spots as well. Finally, the most prominent one is taken in the same seagrass area a couple days apart from the previous image that we saw. And again, we see something notably different that wasn't there previously. This leads us to believe that it's properties of the water itself and not of the seafloor. So with that in mind, we're going to go through the questions we want to address and why they actually matter and why we care about them. So first, we want to know if we can estimate internal wave properties from the SAS imagery itself. That's important because if you know properties of the internal wave, you might be able to determine transport, how it relates to that, how it can relate to turbulence, things of that nature. Next, we want to look at if the internal waves have a measurable effect on synthetic aperture sonar imagery. We want to know how our sonar performs, if it's performing less than the ideal case, and if we're able to know how our sonar performs, there's potential to compensate for that in post-processing. We're going to look at methods of quantifying that. How can it actually be quantified? And if it can we localize it to certain points on the seafloor? And lastly, we're going to look at if we can accurately model the effects of the internal waves on synthetic aperture sonar. We're going to use that model in order to see if we can possibly invert for bolus parameters just from the images themselves, and then later on use that to potentially compensate for the effects, remove them, or determine how the internal wave would play a role in oceanographic body. And obviously, we're going to verify those models with our observations, because frankly, if the model doesn't really agree, then there wasn't really a point to modeling it in the first place. And spoiler, for most of these questions, the answer is yes. Otherwise, I also wouldn't be up here. So we'll start with a brief background on internal wave boluses. The effects that we were seeing in the image are effects caused by the internal wave bolus. The bolus itself is not visible in the imagery, merely their refractive effects. But for internal wave boluses themselves, in our stratified medium, that is the ocean, we can have internal solitary waves propagate. Think of just one wave that travels between the body of colder density or colder water, lower density, with higher density, excuse me. And above that is warmer water with lower density. And as those internal solitary waves propagate towards the shore, they experience a change in boundary conditions, much like surface gravity waves, we have internal wave breaking, then we get our internal wave mixing, and the result is a bolus that propagates up the slope. It's important to note that a single internal solitary wave can result in a multiple train of boluses that propagate up the slope, and internal solitary waves themselves come in packets in their own right. So usually we get a number of boluses propagating up for a set of internal solitary waves. On the bottom, we see a GIF of what that propagation looks like up the slope. And in summary, density stratification leads to internal waves, and as they're breaking, leads to boluses. That's great. So now let's see how we can attack that first question, which is, can we measure or can we estimate properties of the internal wave bolus just from the image itself? To do that, we're going to take a brief detour into space and look at parallax. Parallax is commonly used to measure the distance to distant stars. The basic premise is you take two observation points of a known distance apart, and you look at the same point in the sky, and you get an apparent left-right shift depending on where you're looking at the star with respect to distant stars, and you can compute a parallax angle. And then if you know the distance between your two observations, you can compute the distance to the point. In the GIF here, we see what that left-right shift will look like as we look from two sides of the sun or towards our distant star. Now, how does that apply to internal waves? So to do that, we're going to take our take a look at multi-look image processing. So in basic terms, we take our total image produced by our sonar, take the 2D Fourier transform, cut it into a number of sub-images. And then when we take the inverse Fourier transform, we have a number of sub-images, each one corresponding to a different point along our sonar's path. And then we can look from two different directions to effectively create that parallax measurement. So by taking two different images, we can then compute the disparity between them. So the difference in that apparent shift from our left image and our right image. And from that disparity, we can compute the distance from where the bolus is to that bright focused region on the seafloor. Then we can assume a sound speed inside the bolus and compute an effective refracted angle. As we go through a medium at different sound speed at a different angle, our ray is going to bend towards the seafloor. And that effective refracted angle is the maximum angle at which we're refracting while we still enter into the focused region. So if we look at our bottom little cartoon diagram, the angle between the this arrow going up and the bolus that we make here in our refraction. And from that, we can compute the height of the bolus, since we know the distance and we know the height and an angle. Now we apply that to our data. So here we have our original seagrass image with our internal waves, and we chop up our image into 9 sub-images of band 2 and band 9. Band 5 are the one we're going to look at. Band 2 is looking at from the left side of the image in the along track path, and band 5 is looking from the right. And we can see an apparent shift that will show in our image anaglyph. The image anaglyph is the superposition of both the band 2 and band 5 images. So you see a greenish and reddish color depending on which way we're shifted. If you had the blue and red glasses from the old 3D movies, you would see a bit of a pop. But then from that, we can compute our disparity shown in the top right. And we see the internal wave artifacts are shifted with respect to the look angle that we're looking at. Then we can compute the distance and get an estimate for the bolus height, which on average is about 1 to 3 meters in height. Sometimes exceeding that, going up to 4 and 5, but those are more of the extreme cases. And these estimates are in line with what is typically seen in the ocean. It's also important to note that some things such as shadows will also appear in our disparity measurement because those will also have an apparent shift depending on the direction that we're looking at. A good example is the drag line that we see in our image here. It shows up as a false positive bolus measurement. Although that shift is still there, the estimate for the bolus height is not. We can do this over a number of images where we have our internal waves. So we bring up the same one we saw previously. In this case, we divide it into 8 sub-bands and take a look at band 2 and 6, since those produce the highest disparity between them. Compute the distance disparity and get an estimate of bolus height. Again, we fall within the range of 1 to 5 meters. Lastly, we'll look at one more image. Again, 8 sub-bands. In this case, we're looking at band 2 and band 7. And just to show that we're not exactly cherry picking and it's not a foolproof method, this one clearly performs worse than the other ones. They use a lot more scattered sense of disparity. This can be a result of the effects not being quite strong enough or the shift not being strong enough between our 2 sublooks to actually show a high amount of disparity and get an accurate bolus height estimate. But we can get an estimate that's fairly accurate and agrees with what we would expect from internal wave boluses that form in the ocean. Great, so moving forward then, we want to know if they have a measurable effect on our sonar imagery. We can see clearly the effect. We get high intensity regions in places where internal wave artifacts are present. And we can conclude that they're not a property of the seafloor itself. That qualitative measure is nice, but we want to know if we can quantify that in any way. So to do that, we're going to take a brief detour and do a bit of a background on regular sonar and then synthetic aperture sonar. The next 2 slides are courtesy of Alan Hunter from University of Bath. And they do a very good job of explaining the difference between side scan and synthetic aperture. So for side scan sonar, we have our side looking narrow beam, and we produce our generic raster intensity image as a result. And we get the traditional range varying along track resolution. As we go out, our beam spreads and we get a resolution in the along track that depends on the range. Synthetic aperture sonar is very different in that regard. Synthetic aperture sonar operates by taking a coherent sum of pings as our sonar platform moves into long track direction. And that generates what is effectively a very long synthetic aperture. The benefit of that is that we can get a range and frequency independent long track resolution. We make an aperture that is longer and increases with our range, and thus we can remove the frequency and range dependence from our long track resolution. The downside of that is that we need to have a very accurate measurement of the sonar platform position, because any shifts in that can make us deviate from our ideal linear path, and thus affecting our aperture size. And to compensate for that and motion of the platform, micronavigation has been really helpful. That's simply just compensating for small motion effects that may affect our final image. Synthetic aperture sonar also makes a constant sound speed assumption. So the sound speed is the same at the platform as it is throughout the entire beam. And we can see how that will affect our overall image quality, because internal waves inherently will break that constant sound speed assumption. And so what are the consequences of those being present in the image? The first we saw was fairly obvious. We get bright spots and shadows in the presence of internal waves. As we hit the top of the internal wave bolus, we get refraction down, and that refraction is stronger as we hit the top of the bolus compared to hitting lower in the bolus itself. So that's one of the effects. So we get a geometric lensing effect as the bolus behaves like a weak lens, and then we get an effect from the change in sound speed itself. And that will result in, and another effect is image defocusing. So that will be manifest in a loss of a long track resolution by breaking sound speed, constant sound speed assumption. And the bottom cartoon, we can see just how that is going through the bolus itself. And it's the same, those are the effects that we see physically in our images. We're going to focus on SAS resolution, as that will be our metric for determining the image quality. So we have our long track resolution, that's range and frequency independent, and it's only a function of the element size d. Our range resolution is the standard range resolution that you see in traditional sonar, related to the speed of sound and the temporal bandwidth of the system. Note that the long track resolution is not a function of sound speed at all. So you might be asking, how does a breaking of the constant sound speed assumption lead to a loss of that resolution and not the range resolution? The answer to that is that the long track, the breaking of the constant sound speed assumption in the presence of the internal wave bolus alters the imaging geometry of our system. So that collection geometry is changed from our ideal case, and thus we get a loss in resolution. The effects of on the range resolution are minor, because the change in sound speed that we observe inside and outside the bolus is typically on the order of 2% of that of the sound speed at the platform. And our temporal bandwidth, if we recall, is 30 kilohertz. So if we think of a change of from 1500 to 1530 meters per second of sound speed, that effect is very minor and not very prominent in the range dimension. So we know we're going to use the resolution, but we need to somehow measure that in our images itself. So to do that, we're going to use the point spread function. The point spread function is the response of a point target within our scene to an incident signal. So for a point target, think small rocks, things that will reflect in a close to ideal way that we can get our resolution out. The resolution, or the point spread function, exists in the range and a long track dimension. And notice that the inverse of our sonar resolution is present in the point spread function, both the range and long track. So we're able to use that as a proxy for resolution estimation. If we can find point targets within the scene, we can extract the point spread function from them just based on intensity and get an estimate for the resolution. So now we're going to go through a recipe for that. First, we start with normalizing the single look complex image. So we take our complex SAS image that's returned to us from post-image reconstruction, and we normalize by the magnitude. If we recall, the focusing that occurs due to internal wave presence would inherently bias an intensity-based method of point target detection if we left that in there. So we need to normalize using a median filter on the order of the internal waves to get that out. Next, we would select a region of interest and upsample. We upsample in order to get a better estimate of the resolution itself. And we account for that when we do our final computation, because if we upsample our image, each pixel no longer corresponds to the real world estimate or real world distance that normally would. Then we find local maxima in the image and isolate points greater than 3 standard deviations from the mean. We do that, point targets are expected to be have a higher intensity response than other points of the image. So we're going to look for those specifically. We apply an edge detection scheme and we label distinct points. Edge detection will find the edges of the high intensity points. And if the surrounding points are within a certain threshold, we cut those off and we keep the rest. Then we compute the 3 dB down contours, which we'll use to minimize the difference between our fit ellipses. The ellipses are being fit with respect to the point spread function. And the difference between those is minimized in order to make sure our ellipses can be used to compute an accurate estimate, or as accurate of an estimate as possible for our track and range resolution, which will use the semi-major and semi-minor axes of the ellipses, depending on the ellipse orientation. And then we can compute the average resolution. So what does that look like for a sample? We take a very small image that we upsample. We get our binary edge detection image, which nicely fits around the 3 dB down contours of our bright spots. And then we can see our ellipses being fit over the same areas, and they fit relatively well with the contours. So then we can apply that over our entire region of interest. This is a subsample of the seagrass image on the left in the absence of internal waves, and on the right in the presence of internal waves. So for the absence of internal waves, we get roughly, on the bottom 2 graphs, we show the resolution degradation in the range and a long track dimension. By degradation, we mean the resolution that we're estimating divided by the ideal resolution. So 2 is 2 times worse resolution, 3 is 3 times worse, and so on. And the range resolution is roughly returning 1. So we're achieving close to the ideal range resolution in the absence of internal waves. The along track degradation, even in the absence of internal waves, is roughly about 1.5. So there could be something in our image itself that's causing a loss in resolution that isn't related to the internal waves. The scatter accounts show the number of point targets that are within each averaging bin. So to produce the 2D map that we're seeing, we divide our range and a long track dimension to number of bins and average the resolution estimates from our point targets in there. And we do that to make sure we have a statistically significant number of point targets so we're not influenced by outliers. Then we can look at an image with internal waves, and we see in areas of internal wave activity, we see a much worse resolution than the surrounding areas. And that effect is more prominent in some of the subsequent images. Something else we can do is compute the resolution loss as a function of range. So in areas of internal wave activity, we see a spike in the along track resolution. Then what we can also do is do that for a number of subsets of our image and produce a full image map, what the resolution looks like. This is just for the along track case, since most of the effects were in there to begin with. And you can see in high areas, in the bright spots of the image where the internal wave effects are the strongest, we get the worst resolution. We could do that over a number of different images. So here's another one from the survey, and we highlight our region of interest in our red box. And we show the along track resolution is again worse in areas of internal wave effects. And then we get the peak in our resolution loss at about the spot of the internal wave. And again, we can create a total overall image from this. We can do that again for another image. And again, in areas of internal wave effects, we see a loss of resolution. And then finally reproducing that. So we know that we can now quantify the effects. Now we want to know if we can model them. And again, modeling is fairly valuable in certain cases. If we can see our resolution loss, can we predict that from known bolus parameters? We want to understand our sonar performance in suboptimal conditions. And then we can potentially compensate and remove those effects and potentially invert for bolus parameters. So I'm going to walk through two models. One is numerical involving ray tracing, and the other is analytical, which I will try not to kill you by boring you with math. So first, we'll walk through the ray tracing model. It's commonly used in acoustic measurements or acoustic modeling. So first, we'll simulate an image with an internal wave bolus present. We'll track the ray paths and compute the timings as they propagate to the seafloor from their starting location. Repeat that for a number of azimuthal sweep angles, and then we can compute the ray timing as a function of sweep angle, and we can get the resultant resolution loss. And repeat that for a number of bolus sound speed differences or bolus heights. This is how the geometry of our ray tracing breaks down. We have a 2D slice of what we'll be looking at. The incoming acoustic rays are in blue, and we can see at the top they refract towards the seafloor. And this is our sonar platform, and we'll do this for a number of azimuthal sweep angles or a fixed grazing angle. Realistically, we're incident to the seafloor about 5 degrees, sometimes higher, sometimes a little bit lower, but so now we can see what the ray timings look like. So for 10 degrees of incidence, so the first point in our at our sonar's path, we see the ray number and ray travel time. Ray number is just a proxy for which ray is going through, so the start time of the ray. And we can see that rays that intersect at a higher point at the seafloor or with the bolus have a larger effect on their overall travel time. And with increasing differences in sound speed, we get a greater effect. Then we can look normal to the bolus. So as our platform is now in the center point, going directly normal to it, the effects that we see here are much more prominent. The shape of the bolus is effectively changed depending on the angle that we look at. If we look from a wide grazing angle or a wide sweep angle, the bolus is effectively broader, and that geometric lensing effect is mitigated, as opposed to when we're looking through it at a normal instance. So then we do that over a number of sweep angles. This is the travel time for one ray as we go from one sonar position to the opposite end. And we get that traditional parabolic shape that we see from collecting sonar data, just inherently as the distance changes with our sonar platform. And we take the difference between the timings between a presence and absence of a bolus, and the quadratic form of this and the quadratic phase error that's associated with this is directly related to the loss of resolution. So the parameter that we see here manifests as a phase error in our sonar system, and from that we can compute the loss in resolution. So we do that for a number of sound speeds, for a number of boluses, and the resultant model is this. So we get obviously an increasing loss in resolution for increasing sound speed error. And the bars around 10 and 30 are roughly where we would expect a difference in sound speed to occur, are common sound speed differences inside and outside the bolus. And we're falling at roughly 2.5 to 3 times worse resolution in the presence of internal waves. If we look at our sound speed profile from at around time and place of the seagrass image that was taken in the presence of internal waves, we're at roughly 20 meters per second of sound speed difference inside and outside. Then we can also do it for a number of bolus heights. So for increasing bolus height, we get a worse resolution as well for a fixed sound speed. However, the bounds on the change in bolus height are much smaller than the effects shown by the change in sound speed, showing that most of the effects are likely to sound speed itself, and bolus parameters are less important. Now we'll walk through an analytical model for the resolution loss. And this was done based on some of the work done by Dan Cook and Dan Brown. And some analysis of other strip map phase errors in synthetic aperture sonar. So to start, we take our ideal signal, the two-way propagation to and from the seafloor with an amplitude set to unity. K0 is our standard wave number, and X and Y are our range and a long track position to the target respectively. Then we can take that ideal signal and introduce some deviation from the ideal case and call that our observed signal, where we have delta K and R prime. Delta K encompasses the change or the error caused by a difference in sound speed, and R prime encompasses error in range error and a long track positional error. Then we're going to go through a series of series of reductions through the algebra jungle. I'll spare you the 3 months it took me to get through that and just walk through the end. We do some binomial expansion, a change of variables, and the result is breaking up our observed signal into the bottom function, and we can further break that down. Notice the first part is just our ideal signal, which is the whole point of doing this, to get that out and separate it from the portions with error present. The next only has a range and a long track positional errors. Note that there's no delta K, which would encompass our change in sound speed. The next only encompasses the sound speed errors. Note that there's no factor of beta or factor of gamma. And then the last is a cross term that contains both the range and a long track positional errors and our delta K. So then we can call that the error present in the received signal, G of X and Y. So great, how does that help us? Well, we want to know the phase error that's associated with the change in sound speed. So we can take the Fourier transform. In this case, we're only going to look at the Fourier transform in the long track direction, since that's where most of the error is occurring. And the result is this large function. So to just briefly recap what this function is going to have, the amplitude here is often ignored. Then we have this rectangular function that is new, that appears. This rectangular function is related to the spatial bandwidth of our system in the long track direction. And the spatial bandwidth is then directly related to the loss of resolution from the point spread function. That rectangular function appears since it defines the region of validity of our analysis to begin with. Then we can do that. We can then plug in a number of sound speeds and a number of different bolus heights to produce another model of what we expect to see. And again, we see an increase in resolution loss with increasing sound speed difference, and an increase in bolus height also causes an increase in resolution loss. And we're also at the same order of magnitude of our ray tracing estimate and the estimates we see from the image via our ellipse fitting method. And the good thing about doing an analytical model like this that separates the effects of sound speed and the effects of bolus height is that you can then compute an estimate for resolution loss for every sound speed, for every bolus height. And as a result, you can get some contours. It's kind of a preliminary step in an inversion method, where now for an under-constrained problem such as this, if you know 2 of the properties, you can get the third. So if you know the loss of resolution and sound speed difference, you're able to get the bolus height. If you know the bolus height and sound speed, you can see how much worse your resolution is likely going to be. In tandem with our analytical model, we can look at beamforming over some synthetic imagery. Beamforming in this case is just simply image reconstruction from our artificial echo data. How do we process that to produce our final image? So on the right, we see what our raw echo data looks like. And we have a known point target at about 100 meters in range and 100 meters in our long track position. So right at the center of our image. So what we can do is beamform over this data, apply a phase error as an effective change in wave number. That's from the internal wave bolus being present. Extract the point spread function, and then compare that to what we would see in the absence of an internal wave. So we'll look at how the beamform data looks in the absence of error, and then with error. In the absence, we see pretty efficient along track compression, and our point is located directly at the center with very little smearing of how it looks. On the right, we see a much less efficient along track compression, and our point is now expanded over a bit of distance. We can then look at how their point spread functions compare. Notice the range is not very affected at all by the presence of an internal wave bolus, while the along track is notably broader. Notice the side lobes aren't very different, and we don't expect sound speed to affect that. And we can take a bit of a zoom in, and we look at the range error. Again, there's not very much, and the along track point spread function is notably broader and worse. So then we can do this for a number of sound speed and bolus heights again, like we did previously. And we see the similar trend with similar order of magnitude as we saw in the previous model and that observed before. Notice there's a bit of variation in these models. That's likely a result of sampling constraints and some of the interpolation methods used in image reconstruction itself. Now we'll compare all of those just to see how they perform against each other. And they agree relatively closely in their order of magnitude and their general trend. There's some deviation. There's some differences in the behavior of the along track resolution loss as a result. It's a function of sound speed. This curvature from the ray tracing model is likely a result of some aperture effects that are included in that, but possibly ignored in note. Similarly, our resolution degradation as a function of bolus height shows a linear behavior from ray tracing, however, quadratic in our other models as a result of what we select for that parameter of beta in R that encompasses our range of track positional errors. But they agree fairly well with each other. So this would pave the way for something closer to inversion or removal from our error to. So we'll now recap some of the questions we addressed throughout. Can we estimate the internal wave properties from SAS imagery? Yes, we can do that. We can use some multi-look analysis to get a rough estimate of what the bolus parameters would look like. We can show that they have a measurable effect on synthetic aperture sonar, quantified using the resolution and estimates from point targets within the image itself. Using their point spread function, we can get a proxy estimate for the resolution itself. Then we can accurately model them through a number of different methods, which will lead to, in the future, if future studies would look at full inversion methods just from the images themselves. Con, if you need a new project, by all means. And the models agree fairly well with observations. At this point, I'd still like to, again, thank everyone for being involved and being very supportive, my parents as well. And with that, I'll take any questions.
Questions, and I'm including the online folks. So Chris, I guess you can see people if they've sent in some chat questions.
Sure.
So I'll let you pick and choose who you want.
I think you may have gotten into this at the end. That homework needs to be done. But did you actually apply the correction to the original images and see if you reduce the amount of artificial or artifacts that we see in those images?
I did not. That would be a good thing to look at in the future. Yeah, definitely. We did look at potentially prior to image reconstruction, introducing or correcting for the timing errors and seeing which one would produce the best quality image, but that would have required some other data that we don't have access to at the time. Jenna?
So I'd never heard of boluses or boli until you talked to me about them. And I didn't catch at the very beginning how you said you identified these as the presence of boli instead of just sand ripples. Like, how could you tell?
Sure. So in the case of the seagrass image, it was fairly obvious because it was the same region, just a few days apart. You were seeing these ripples.
Okay, and that wasn't likely to be caused by any sort of like tidal or currents going on.
Not.
Or it was in the seagrass that it looked like.
It was in the seagrass as well, but it couldn't really have been tidally driven. Granted, internal waves and internal wave boluses are tidally generated in some cases, so
okay.
There's that as well. But
and then kind of related to that is for the assumed constant sound speed in these features, how would you choose the sound speed? Like, is there a CTD profile that you would base the solidity on?
So there's been some work that incorporates a CTD profile into the imagery construction itself. But most often there's a measurement at the platform. So the AUV that the system is mounted on, it'll take a measurement of the sound speed there, and we use that throughout the entire imagery construction.
Do you see this being applied to correcting for sound speed errors in multi-beam data, for example?
Yeah, because certainly these effects would still show up in multi-beam data. So it could be applied. I'm not as familiar with image reconstruction for standard sonar systems, but yeah, if it's all just timing based, you can use it to do the same things. Yeah, Tracy.
That's right. I just have questions about the environment you're working in. So, like, what was the water depth? Like, how big was the seagrass bed? Like, I haven't ever really seen internal waves around seagrass, so it's very interesting.
Yeah, Water depth was roughly 50 meters throughout most of the survey, I believe. The size of the seagrass bed in total, I know that image was fairly large. I'm not entirely sure how big the total seagrass bed was itself. I wasn't involved in data collection at the time.
And this was around Italy?
Yeah, off the coast of Elba Island, Italy.
Elba?
Elba. I
These
can,
are, they can be big.
Yeah,
So these are not internal waves. These are after they break.
yeah.
The horizontal scales he's showing here, 100 meters. We have some images that are half a kilometer to a kilometer. They're linearly coherent. So they're cool pictures that move a lot of cold water.
I've seen it around kelp forests a lot. I've never.
So one of Nick's committee members is not here, and he left a bunch of questions, most of which I'll ask after you guys leave. I'm going to ask you one that I think is good. It says you looked at the bolus with the crest parallel to the vehicle track.
yes.
Speculate on what would happen. You've already talked about this, I guess. If you're 45 degrees or orthogonal.
Yeah, so I suspect not very much would happen if you're orthogonal to it, because at that point, you're going to effectively be looking through just a 2-layer medium at that point. The refraction you get from going through the top of the bolus, that peak, is just going to be much less prominent. And that's where most of the timing error occurs. If you were to take just a 2-layer medium, if you recall the ray number versus ray travel time as we go through the bolus, it would be very close to 0 difference between that and the absence of an internal wave. So that's how that would.
These are actually 45.
Yeah.
Questions online? Questions in
I
house?
looked up there. I can't see it.
We went significantly under an hour. Good job.
40 minutes.
I know. All right. If there are no more questions, I have one more. Sure.
So these boluses obviously have a lot of turbulent mixing, and you're kind of treating them as like a single thing like this. How do you think the turbulence affects everything?
So it would greatly change the incident angle that we're approaching at if we think of it as a rough surface instead of just a smooth boundary. So that would likely increase the amount of refraction or decrease if it makes it more normal to the incident ray. So things like that could occur.
Sorry if this doesn't make sense. I don't really know much about boluses either, but you tested for different bolus heights. Would shape be something that would affect considerably?
Yes. Yeah.
They come in a big variety of.
Yeah. So previous studies like in lab showed a ratio of height to length of 0.3, relatively constant, plus or minus a few meters about that. So that's what I did or tried to maintain for the majority of the modeling because there was some base premise around that. Picking a bolus, you can make it flatter and more hemisphere in nature. You would still result in the same effects, just to a lesser extent because we have a flatter top.
Could you be more concave and completely change how you're
concave in the sense that the top is.
Yeah.
I don't think that.
Okay. We're waves or.
Yeah. Anna. Oh, sorry.
I was wondering, like, you can have, if you're in a different setting in an environment that your extremes of what you're bringing in cold water underneath usually with an internal wave, right? Like, and then these guys are breaking. If that temperature difference is much larger than you have here or smaller, how do you think that would affect what's going on? Either, yeah, there are lots of things, ways to answer that question.
Yeah.
I'll let you answer.
Yeah. So the if we end up with more extreme sound speed differences or temperature differences, we're just going to see more extreme loss of resolution. I would expect. Yeah. Does that answer your question?
Yeah. Do you think that would affect the kind of turbulence going on there and the way those waves change, or do you think that would just be just the physics of the interaction of the wave breaking in that setting?
I don't suspect much of the underlying generation would change. Maybe they would be, maybe the resultant like bolus size or shape would change as a result of the greater difference in sound speed initially with the internal wave, things like that.
Do you think you'll be able to apply these methods real time? Say you're using the sonar data on an AUV that's maneuvering and it takes these boluses and thinks, oh, this is an obstacle in my way rather than just some sort of wave phenomena. Do you see this being applied real time someday?
Potentially, I'm not sure if the SAS image reconstruction is typically done in real time. I'm just not as familiar with that. So if that is, I can't imagine why correction methods couldn't be applied at the same time too.
I'm going to build off your question in a very strange way. So you said the frequency of your system was 100 kilohertz, correct? The center frequency? That directly overlaps with many species of dolphin echolocation, which are also living sonars. Do you think these types of waves and artifacts from the internal waves is something that biology has to deal with as they are going through their life and foraging?
As far as the biological implications, I'm not that familiar, but the effects that they have with respect to transport, they're obviously going to be bringing up nutrients from lower depths as they break. So that could impact things like foraging and food supply and nutrient supply. As far as communication and things related to that, I would say no, because we are in fairly shallow water compared to other areas, because it is only 50 meters. Yeah.
She might have meant if they're searching
Yeah,
and they have a
that goes-
refraction, they're going to miss what they're supposed to.
Oh, that's what you mean.
Yeah.
So do they have some ability to do what you're doing naturally? Could it be possible, or is what you're doing?
It'd be really cool if they did. I don't know.
I would love to know.
Yeah, that would be.
I don't even know how you would test that, but maybe dolphins, I guess you could test. It's just that's the whole time we were talking, I was thinking about biology has to deal with this too. It's not just humans that are trying to learn about their environment, but the biology that lives in it too.
So,
Coming at it from a different perspective.
no, that's fair.
During these tests, they had similar tests. These tests, they had the animal seals there. Pineapple seals.
They don't echolocate.
I wouldn't be surprised. Nature does things better than us usually anyway. So
I'm going to cover my ignorance by saying, any more questions?
So what is I understand that time or internal waves move slower than regular waves on the surface. What's the lifespan of these boluses staying at I mean, some of them were 3 meters tall, right?
yeah,
Would that does it propagate, or would the propagation of those boluses affect your time series of mapping data, or you have to apply the resolution corrections frame by frame basically?
yeah. It depends on the image collection process and the internal wave itself. Their time scales of travel, they're roughly 10 centimeters per second, and our sonar platform is traveling at 2 meters per second. So that difference occurs there as well. But
If you show the images from the multi-look, they can be different.
Okay.
So it does.
Sorry.
Yeah.
Very cool.
and yeah, they do propagate fairly far up as well. So
10 centimeters per second is kind of long.
Yeah. Relative to those.
I have a question. So you looked at boluses, and boluses really have a pretty small radius of curvature compared to the original internal waves. So do you envision any effects, whether focusing or image degradation due to the focusing through the original internal wave?
yes, but much lower. Because the refraction is just going to be less. You could inherently treat it as a 2-layer medium depending on the wavelength of the internal wave. So you'll end up just going through it and bending through, and then you could just compensate for sound speed without having to worry as much about the refraction.
One question?
So you had said
got one
there
more?
was some tree work done by Steve.
Yes.
I'm just curious, where did you pick that up from? like how much pre-work was done when you were doing that with review? How did you springboard off that?
For the analytical model development, you mean?
Yeah, exactly.
Yeah, the method was followed fairly closely with how they did it. If you just take a received signal, you could introduce an arbitrary phase error. So linear, quadratic, sinusoidal, the sawtooth phase error was done as well. Yeah.
Apologies if you answered this already. Once you've estimated the bolus height and orientation, can you generate a better estimate of the 3D sound speed environment?
From which part was that referring to?
That's a great question. I don't know. That's all it does.
Because if it's from the initial multi-look analysis, if we're assuming a sound speed and the bolus height, once we assume a sound speed and a bolus height, if prior to that we assume the sound speed is constant, we'd be able to effectively generate a sound speed profile, but it wouldn't be very robust. It would be more constant sound speed. We hit our bolus and we assume it's the same throughout, if that's what that is referring to.
Heck yeah. And can this be reapplied in processing to improve the bathymetry results?
Sure, yeah, of course.
5-minute break.
Sure.
If the two committee members that are here need to take a little 5 minutes. Or Dan.
Hey.
Everybody out except Dan. Bye, everyone, thanks.